Hi, my name is Dr. Joshua Humberston. I'm the director of the Coastal Hazards Lab at the Atlantic Resilience Innovation Institute, also known as ARII, much easier to say. ARII is a 501c3 nonprofit organization focusing on advancing how our communities in both Massachusetts, regionally on the east coast of the United States, and even beyond, deal with the impacts of coastal hazards and build more resilient communities. Two approaches we take to this are workforce development. Our Coastal Academy, led by Jeff Granantino, is an academy for kids mostly coming out of high school to learn the fundamental skills they need and get an internship in the resilient workspace, to understand how they can get a foot in the door quickly and become part of that very much needed workforce to solve resilience challenges. The other part of it is the Coastal Hazards Lab that I lead, where a group of scientists and engineers conduct science, works with our partnerships in academia and industry, and really is focusing on accelerating how we get technology out of the labs and academics into real world use cases, because our challenges facing coastal hazards are greater than the solutions we have right now, but we have the ability to change that. I'm here today because we're starting a small series called the Learn the Science series. It's about showing you a little window into what happens behind the science, the figures that you see. How do we get there? How do we think about problems? How do we come at this problem and say, how do we make it very objective and actually quantify the issues that we see more directly? I wanted to start out with a topic of great importance to me: numerical modeling, simulation, digital twins. And you might not know what all these have in common or if they're the same thing, and that's perfectly valid because there's been a lot of confusion. Numerical modeling is this idea of using computers to discretize physical systems and represent them in a digital space. It's frequently similar to simulation and sometimes the same as a digital twin, but digital twins tend to be a coverall. Something that can cover something as basic as a computer-aided design model of a car, but it could also be a sensor network like we have at the Coastal Hazards Lab, or it could be a numerical model. Today, we're going to spend a little bit time talking about numerical modeling, what it is, and what it means for ocean science and coastal hazards. So since we are a Coastal Hazards Lab, let's start with water. What is it? How do we think about it from a modeling perspective? Well, I'm sure in your high school chemistry class, you learned about water as H2O particles that are interacting, can be a solid, liquid, or gas, and that's all correct. And when it comes together, it forms a large liquid substance like the ocean, what we see here on the left, and this can have waves that can be driven by winds, could be driven by landslides, many different factors. And the behavior of that water, the wind, the way it moves, the way waves form, is actually not just that surface expression. If we look here on the right, we have the atmospheric component above the water, the surface itself, and then the underlying physics below the surface of the ocean that are all contributing to its behavior. What's important to know about from a modeling perspective is, even as advanced as computing has become today, we cannot perfectly simulate the molecules of water in even a single glass. It is hopelessly complex, and it doesn't get us very far even if we do it. So from a modeling perspective, we say, how can we represent these systems by scaling down the complexity, understanding their behavior, and then coding and modeling it so we get it close enough even if it's not perfect. And so don't be scared off by the equations here on the screen, but one of the simplest ways we can do it for the ocean is using the shallow water equations, which are derived by the Navier-Stokes equations. Again, don't worry if this doesn't make sense, but this is a set of hyperbolic partial differential equations that describe the flow below and potentially the surface expression of a pressure surface in a fluid. You can think of it this way: we have different terms in here like the depth of the water, the time, the X and Y location, Coriolis force, different coefficients. But all these equations work together to describe how water moves around relative to itself. However, when we move from those differential equations, which are continuous, meaning the exact solution at any point in time and space, that doesn't really work well for simulating a large field computationally. So we have to discretize it. meaning we take it and we change it from infinitely small to small slivers where we can actually calculate the values and solutions over time. So we'll have a delta x, a change in x, a change in y, and a change in time. So we end up with small cells or nodes where we can solve those equations in a meaningful way relative to the other nodes in our field. When we do this, it does modify how we look at those equations. So there's several ways in which you can calculate those equations depending on where you solve them, even over a single cell. And those are described by the A, B, and C grids here of where it's calculated. And these are called ARII grids, A grid, B grid, C grid. There actually is a lot of importance for how you solve the equation on a single node for how it will interact with other nodes. For example, if we have the ocean on the bottom right here and a lake somewhere inland here on the top left and a river that flows between them, and there's only one cell connecting them, a B grid won't actually allow water to flow through that area because of where that U and V terms, the flow of water, gets calculated. However, if you use a C grid, you'll see that exchange of water between the two systems the way we would expect. So it's because of this that we'll typically use a C grid while solving the shallow water equations. So before I show you this, I'm going to actually take a look at what this code looks like, but it's just a couple hundred lines of code running in Python, a simple programming language. And if we look here for these Euler 2D and leapfrog schemes, again, it's quite ugly, but you can see these grid schemes A, B, and C. Those are actually those equations programmed in here so that we can run it iteratively over time. And so this program I have, if I actually execute it here, it probably will take it 2 minutes, but the first thing it's going to do is saying, are your parameters set up so that this will be a stable simulation or numerical model? And so we should see that pop up in a minute with any luck. It does run a little slow while I'm also taking video. There we go. Nice. Your parameters should not cause the leapfrog scheme to explode. Then it starts running over those steps in time. And you see that progress happening here, 3%, 4%, and it will run over time to get an idea of what's happening. And so if we go back to our slides, get something like this out of that simulation. So what we're looking at is a representation of the water surface, and I press play here. I'm driving waves on one side of this domain, saying the water level is going up and down. But it is actually those equations occurring over every single grid node you see here at every single point in time that allows those waves to propagate through the domain. Even though we don't understand the molecular level of physics, we get this reasonable expression and approximation of the water surface. And so again, even though this might look a little bit complex, this is again one of the simplest forms of representing a water surface. And so it only gets more complex after that. We're ignoring the vertical cells. So if we're looking at a cross-section of the ocean here, there's a few ways we could introduce vertical cells if we want to understand the dynamics of what's happening under the water. We could have these rectilinear cells, so just stepping up one at a time. We might change our cells to follow density patterns, or we might have changes in our cells depending on what the bottom looks like. And this is one of the most common ways to look at it, meaning you have just as much vertical resolution near the beach as you do in the deep ocean. And in the real world, these model grids only become more complex. Here's one example of a global model where you actually see that the cells are not rectilinear, meaning they're not all perfect squares, because that doesn't work very well on a spherical globe. And so we use these curvilinear grids to model global patterns. We can also use irregular grids, which is made out of triangles that slowly change shape. And what's valuable here is we can get higher resolution near the coast where most of our activity takes place, while not wasting computational workloads in the deep ocean where processes are comparatively simple. Here's an example of a irregular grid for a coastal inland water body where we have larger grid nodes offshore, and it gets higher and higher resolution towards this inlet of interest, and we can actually model it over time. And so this is, again, the shallow water equations are very simple, and as we seek to model more complex system, it requires us to develop models that also become more complex. One example of this is the coast modeling system, which models the atmosphere, waves, ocean, water bodies, sediment transport, all into a single domain. So what this means is that we are looking at the atmosphere as one system, waves as another system, ocean as another system, and sediment as another system. But building this model out so that they speak to each other, that waves can move the sediment around, the atmosphere can generate the waves, and so on. And so you can imagine this becomes a very complex model to run, which is exactly why we end up moving from our personal laptops to high performance computing centers, HPC. These are teraflops of power that we're able to use and run these models in a reasonable time frame so they can actually become useful. But like the AI revolution that everyone is aware of, it is incredibly computationally expensive, which is why we're careful about how we build the models to get the answers we want without excessively using computational power. And the different kind of models may have different ideal use cases. Phrase that a lot of people throw around is by George Box, a famous statistician, that all models are bad, some are useful. This wasn't his exact intended use case, but what he meant was that models are inherently flawed. They are not perfectly representing the system as it actually exists, but rather trying to represent it in ways that are important for a certain use case. So I'll play these two videos here, and what you see is one model is specifically focused about flooding events, inundation of marshes and areas, but it's not doing waves. It's not doing physical processes from the atmosphere, but it might be really good at predicting flooding. In another case, we see a model that's tuned around tsunamis. So it's not focused on tides and other water level variations, but rather how a tsunami wave might come into a harbor, how it'll refract around a coastline. And if we have a city here, it might be particularly dangerous if it comes from one direction and that water wave height actually increases. This model would be very good for, or not very good, it'd be bad for understanding phytoplankton dynamics in the open ocean. Other model types include ones that are focused on morphodynamics, the change in how the actual Earth changes relative to the hydrodynamics over top. So one example here is a river has complex morphology that changes as the water flows through it over time. We also might look at models at a very small scale. So this is individual sand waves, an oscillating fluid surface such as that's produced by waves. And what you can see is individual sand grains moving around over this time. And that's actually of interest because this helps us quantify those very small scale processes that get parameterized in our larger models to make sure that we get them right. So the last thing I want to talk about is validation of models. Models are typically not perfect, especially not when they're first built. They might not have the viscosity of the water right, or they might not be using the right kind of sediment. So we do field validation. We collect real data in the real world and use it to improve our models by turning knobs. And so what you see here is from some work that I did in the Outer Banks of North Carolina by Oregon Inlet, where you see in red the sensors that we put out in the system to measure water level. And the black circles is the closest node from the model to that sensor. When we do that comparison between the observation in orange and the model in blue, we see that this was not the first model attempt. The model performs fairly well compared to observation, but there's time periods where it does worse. For example, this AWAC, acoustic water and current profiler measuring water level, it doesn't do so good during certain periods in the beginning and the end. And so these are areas where we need to turn the knobs and improve how that model performs to match it to reality so that we can then use it to forecast events that we haven't seen yet. Well, thank you for joining our Learn with Science series, our first episode. Really appreciate you being here. Hopefully it gives you a little bit of an idea and a window into what's happening behind some of the science, the computer science that's required, the oceanography that's required, the engineering that's required. It all needs to come together to be powerful in the way that we need to get solutions out there today. If you want to learn more about the Atlantic Resilience Innovation Institute, please head over to our website, atlanticarii.org, and we're happy to chat with you about partnerships or anything else. Take care, and we'll see you next time.